Hello and welcome to this video. My name is Nicholas Norberg and I'm an application specialist for X-ray diffraction at Malvern Panalytical. In today's video, I would like to demonstrate you the functionality of our new Empyrean Series 3 with the new multi-core diffraction setup. And I'm going to show you the functionality by demonstrating it on a sequence of different measurements on very different sample types, applying different X-ray diffraction applications on each and every one of them. And for this, we're going to be using our new Empyrean Series 3. And I would just like to give you a very quick rundown through the setup. And the setup consists of our incident diffraction module, the I-core. And on the diffracted beam side, we have the corresponding D-core setup. Both components are fully programmable optical components that allow you a very easy switch between parafocusing geometry, parallel beam geometry, but even microbeam applications. And that allows you to measure all different kinds of sample types within a sequence in one measurement batch without having to interact with the setup. In addition to that, we have a reflection transmission spinner that is conventionally used for powder diffraction measurements and an automatic sample changer that allows you to measure all the samples without having to load after each measurement. And having said that, I would like just to give you a very quick introduction to the samples that we will be measuring today. And we will start with a powder sample of a cobalt oxide, which is a very relevant compound in nowadays industry because it is used in battery production. After that, we will be measuring silver behanate, which is a metalloorganic compound on which we will demonstrate low-angle diffraction. After that, we will be measuring mesoporous silicate and to demonstrate 2D diffraction at very low angles in transmission geometry. And since we're then already automatically switching to transmission geometry, I would like to demonstrate you small angle X-ray scattering measurements on a titanium nanopowder. And after that, we will be measuring an iridium coating on which we will be measuring X-ray reflectivity, but also grazing incidence diffraction, just to investigate the layer in more detail. And then afterwards, we will be measuring rolled copper, on which we will perform omega texture measurements, which is a completely new functionality that has been added to our Empyrean. And then we will be conducting omega stress measurements on a steel transmission from a car. And all of that will be measured in a sequence without me interacting with the system. So this already brings me to loading the samples in our sample changer magazine. And for these measurements, I have already predefined a sequence using our batch function in the data collector. And I will just quickly show you what this measurement sequence consists of. So I'm going to open this batch measurement program now. The batch consists of predefined measurement programs that are delivered together with data collector, which are optimized for each individual application. And not only does this measurement sequence consist of the measurement programs that I use to analyze the samples, but it also will switch fully automated from reflection geometry to transmission geometry to enable us to do this transmission measurements for small angle X-ray scattering, for example. And it also has a couple of direct beam alignment steps that we need for very precise measurements around the direct beam, for example, reflectivity. So this is the sequence itself. And as you see, we will be going through all the measurements fully automated. And for each sample position, we have defined different measurement programs in advance. And with that brings me to the last step. I need to load the samples before I start my measurement batch. I will just place the magazine inside the Empyrean, into the sample changer, and then I will simply start the measurement from the software. And with that, my work will be done for the next 45 to 50 minutes, during which all the data is being collected. As you will see now, in a couple of seconds, the samples will be loaded. So like here for sample number 1. And this will be followed by our camera that we have here in the background. So that camera can be used for documentation of sample surface effects, for example, that allow you to also investigate after measurements. For example, if you see something strange in your data, you have a chance to just check if the sample surface was okay or if something happened to the sample during the measurement. Then the setup is completely automatically adjusting itself to the specified measurement conditions that I have announced for all these different type of measurement programs. And it will change slit sizes, mask sizes, and it will decide whether it will use parafocusing or parallel beam geometry. And once this is done, then the measurement will start and the data will be collected. And with that, I will just leave the setup to itself. And once the data is collected, I will be back to discuss the results with you. Now that our measurements are finished, I would like to take a quick look at the data together with you and discuss the kind of information that you can derive from data that we just collected. So for this, I will quickly open the data and have a quick run through through each and every raw data set with you, and also quickly discuss the type of analysis with you. So for that, I'm gonna open all the raw data sets, except for the 2D data that needs to be opened separately. And this is the overview measurement on the cobalt oxide that, with which we started our measurement batch. And you see that in the short measurement time that we have a very nice peak to background ratio and very good counting statistics. And in this particular sample, what is interesting is the type of cobalt oxide that is present. So you see this is almost pure cobalt-3 oxide. However, it has an impurity of cobalt monoxide, and this is the very interesting part for this type of sample. And even with the very short measurement time that we had, we can quantify an amount of cobalt oxide as low as 0.2 weight%. The next data set was the low angle measurement. And in this particular measurement, I would just like to quickly emphasize the quality of the background at low angles that allows you to nicely resolve the silver Behenite peak that is as low as 1.5 degrees. And I think this is the only thing that needs to be discussed with this individual samples. So the next data that I want to discuss is the small angle X-ray scattering data. And I want to start with the background measurement, for which I will switch to a logarithmic scale. And you see here, this is the remnant of the direct beam that was here attenuated, this is where the attenuator was switched off. And you see that there is almost no background coming from the sample holder itself and from the beam path. And when we compare this to the nanopowder of titanium oxide that I measured afterwards, you clearly see here a peak in the low angle range, and this signal is the small angle X-ray scattering signal that we're looking for. And from this type of data, you can estimate the particle size of the nanopowder, which I did here on the very data set that we just collected. And this is the result, and you see here that the estimated radius is roughly 45 angstrom, which means we have a diameter of 9 nanometer for this particular powder. The next data set is the reflectivity measurement that we collected on the iridium coating. So this is the reflectivity data, and you can nicely see here in logarithmic scale the fringes that appear coming from the total reflection and interference inside the coating. And from this information, we can very quickly derive and estimate the layer thickness, which for this particular sample is around 44-45 nanometers. And also here you see in the Fourier transformation of the curve, you see that you have a maximum at around 43 nanometers. So the next data set is the grazing incidence scan that I collected on the same iridium coating. And from this kind of data, you could also determine or do a phase analysis. However, what I would like to show you is that you can derive residual stress information inside the coating from this type of data. And this is what I've done here. So this is the analysis of the iridium coating. And you see here is that the individual peaks were defined, and each individual peak represents a different data point in the sine-squared psi plot. And from the linear fit of the slope, you can derive the residual stress information, which in this case is a compressive stress in the area of 2.5 GPa. Then we have the Pole figures for the rolled copper that was collected afterwards, where you can nicely see the preferential orientation of the individual crystallites due to the rolling. And this is the example for the 311 reflection of copper. And also here I have the result of the 222 reflection, where you can nicely see the symmetric features that result from the rolling of the metal. And then we have the residual stress measurement on the steel sample. And this is where we collected, where we determined the peak position of a certain reflection, in this case the 220 reflection of alpha iron at different sample orientations. And from this we can derive the residual stress. And for that, I will just open this analysis. And there you see we can nicely determine the stress in the two individual directions. So this is in the length axis of the transmission, and this is perpendicular to it. And you see we have roughly a compressive stress around in one direction of 450 megapascal and in the other direction around 650 megapascal. And last but not least, I also quickly want to show you the 2D data on the mesoporous silica. So, which we collected also in transmission, where you can nicely see that you can resolve the diffraction ring coming from the mesoporous silica, which has a signal around 1 degree. And also here you see that we have a very good peak to background ratio, and we can nicely resolve this reflection despite the very low angles. And with this, I would like to conclude this video. I hope you found it informative, and that you can and that I could demonstrate the functionality of the Empyrean to you. And thank you very much for participating, and I hope to see you soon. Thank you very much.